Ever wonder why a hot air balloon rises or why a car tires might look a little flat on a cool day? It all thanks to Charles' law. In this video, we'll deep dive into the fascinating world of gases, exploring a life of brilliant scientist Jacques Charles and see how this fundamental law works with the real world examples. It shows the relationship between volume and temperature of a real gas. So at the end of this lesson, you should be able to understand all the properties of gases, mathematical form of Charles' law. Before we get to the law itself, let's do a quick recap on what gases are. A gas is a state of matter where particles are very far apart and move randomly and quick. This is why gases take the shape and the volume of their container. The key variable we are talking about today are temperature, pressure, and volume. For Charles' law, we are going to focus on how volume and temperature are linked while keeping the pressure constant. Remember, gases are highly compressible and they have very low density. So we have some examples of gases here. So balloons has helium, so that is an example of gas. Steam from the kettle, argon and nitrogen. So these all are the gases. The man behind this incredible discovery was Jacques Charles, a French physicist and a balloonist from the late 1700s. He was a pioneer in his field and is most famous for his pioneering hot air balloon flights. In fact, his work on how gases behave at different temperatures are directly inspired by his passion for ballooning. He spent years observing and documenting the relationship between a gas's temperature and its volume, which ultimately leads to the law we are discussing today. So, what exactly is Charles' law? In simple terms, it states that for a fixed amount of gas at a constant pressure, the volume of a gas is directly proportional to its absolute temperature. What does direct proportional means? It means if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. The famous equation is V1 by T1 is equals to V2 by T2. How we got this? As we know, according to the relation, V is directly proportional to the temperature. So we can say that volume by temperature must be constant. So for two different scenarios, we can use this particular equation to get the unknown. Let's see this in action. If we were to graph volume against temperature, we would get a perfectly straight line, showing that as one increases, the other increases at the same rate. Imagine a balloon. If you take that balloon and put it in a refrigerator, the gas particles inside slow down, they don't hit the wall as often, the balloon's volume decreases. But if you take the same balloon and warm it up and particles move faster, hit the walls more forcefully and the balloon expands. Gases at different pressure. The graph shows different slope, you can say. So for different pressures, we obtain four different lines. Just a quick heads up. Temperature must be in Kelvin for this works to correctly. If the temperature is not in Kelvin, it means it can be negative. But in negative, the volume is not supposed to be negative. It must have some volume. So at absolute zero temperature, the gas is supposed to occupy zero volume. According to the Charles law, a gas volume would become zero at a certain negative temperature, which isn't physically possible in this real world. The Kelvin scale is an absolute temperature scale where 0 Kelvin represents absolute zero, a theoretical point where all molecular motion stops. This makes Kelvin the only scale that accurately represents the relationship. Just add 273.15 to your Celsius temperature to get Kelvin. Let us do a real world problem. A balloon has a volume of 2 liters at a temperature of 25 degrees Celsius. So here we have given volume, initial volume supposed to be 2 liters, temperature is supposed to be 25 degrees Celsius. So we can convert it into Kelvin by simply adding 273 into it. So the temperature becomes 892 kelvins. This is supposed to be my initial temperature. If the balloon is placed in the freezer at 10 degrees Celsius, the temperature changes to 10 degrees Celsius now. So I can say it would become 283 kelvins. What will be its new volume? We assuming constant pressure. So again, we can simply solve it by applying the Charles law equation. So according to Charles law, for the same gas at different temperatures, V1 by T1 is equals to V2 by T2. Plug these values into our formula, solve for value V2. So we can say 2 by 298 must be equals to V2 by 283. When we solve it, we get volume approximately 1.77 liters. So this shows that how Charles law works and how temperature changes the volume. You might not realize it, but you see Charles law in action all the time. Hot air balloons, baking breads, car tires, pop-up turkey timers. They all are the examples of Charles law. To summarize Charles' law in a beautiful, simple concept for a gas at constant pressure, its volume and temperature are directly related. Remember the formula, remember to use Kelvin, and you will be able to understand the behavior of gases in different situations. Thanks for watching. And if you enjoy this video, don't forget to like, subscribe, and hit that notification bell so you won't miss our next video. See you next time.